We're going to talk about power series and the radius of convergence. And that first box, it says a function that can be represented by an infinite series is called a power series. It's of this form. This is important, but kind of hard for us to wrap our mind around until we actually do an example. So we're going to jump right here where it says find the nth Maclaurin polynomial. Let's take this one piece at a time. A Maclaurin polynomial is centered at x equals 0, which makes things a little bit easier computationally. And it's the nth one. Normally if they said the fifth one, then we would have, well, 6 terms. Like if it's the fifth term, the fifth Maclaurin polynomial, it would be of degree 5. So x to the 0, x to the 1, 2, 3, 4, 5. This is the nth one. So we're going to have, well, n plus 1 terms. And we're going to write it as an infinite series. So let's just kind of start that idea. And we're going to start by figuring out a few basic things that are going to be very easy, very quickly. First of all, the function itself is e to the x. No surprises there. They told us that. The derivative is e to the x. The second derivative is e to the x. And normally, on a lot of these problems, it's a good idea to do this just to establish a pattern. And in this case, it's the most obvious, easy pattern ever. So let's just kind of quit. And we're going to bring this down and say, well, whatever derivative I want, the nth derivative, it's just e to the x. Okay? Now, what I'm going to do is plug in 0, and why 0? Because it's a Maclaurin polynomial. Maclaurin polynomials are centered at x equals 0. So we're going to say, well, f of 0 is 1, and f prime of 0 is 1, and f double prime of 0 is 1, and the nth derivative, when I plug in a 0, is 1. And we're doing that just to establish a pattern. Now, a Maclaurin polynomial follows this form right here. So it's kind of right. And a Taylor polynomial does too, only Maclaurin is centered at 0. So whatever degree I want, and I'm going to call it n because that's what they told me to do. Whatever degree I want, I'm going to put f of 0 over 0 factorial, x to the 0. This stuff is superfluous. And then f prime of 0 over 1 factorial, x to the 1. And then f double prime of 0 over 2 factorial, x squared. And very clearly we notice the pattern, we know what's going on. And this is going to stop when we get to the nth term. So we're going to have the nth derivative, and that would be n factorial over x, or times x to the n. Okay. We could kind of work through some of this, and we will. But as we do, we notice that we basically have 1 over 1 times 1. So this is 1, obviously. And then this is 1 over 1 times x. And this is 1 over 2 x squared. And then this next one, which would be the 3, is going to be 1 over 6 x cubed. And we just continue with this idea until we get to this. The nth derivative, when you plug in a 0 of e to the x, is 1. So 1 over n factorial, x to the n. And this is the general form right here. This is our general form. So if I wanted to make an infinite series out of this, let's suppose that n just goes on forever, then I would really say, well, what I have is the sum from 0 to infinity. See, started at 0, counting all the way to infinity, of whatever the general form is. And the general form is what happens when I plug in an n. So that's this one. Because when I plug in 0, I get this. When I plug in a 1, I get this. When I plug in a 2, I get this. When I plug in a 3, I get this. When I plug in a 4, blah, 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 blah. Well, the general form is just when I plug in n, which would be that right there. Let's put that x to the n in the numerator. So x to the n goes here. And we have n factorial. And we have actually answered the question because they said find the nth Maclaurin polynomial for e to the x and write it as an infinite series. So here is the deal. This is an infinite series. It goes on forever if n goes out to infinity. So this goes on forever, and what is it equal to? E to the x. So e to the x is this. No one ever told you that, right? So all that I put in this little red box right here, this is e to the x. Now it is, here we go. Now we get to the meat of the lesson. It is an approximation for e to the x depending on how far out you take it. But if we go all the way to infinity, is it a perfect approximation? if we could somehow go all the way to infinity, would this always, for every x value, be a perfect approximation? I don't know. Let's see. So here's what we're going to do. We're going to talk about the radius of convergence. And what I have here is exactly what we just did. So first of all, what you see, and I'm going to make it a little bit bolder, just so it'll show up better. What you see right here is e to the x. Okay, there's the graph of it, and you know what it looks like. This is our approximation. I have it turned off, and clearly I can't go all the way up to infinity in real life or on a computer. It just doesn't do that. Now we can approximate, but we can't truly go to infinity. So what I'm going to do is turn this on. Actually, let's back it up here. So if I was to count to 0, then this is my approximation. We've been through this when we went through Taylor series. This is the worst approximation ever, except at that one point. And so then we will change it to a 1, and then the higher order polynomial we go, the more terms we have, and the more terms we have, the better the approximation gets. So now it's modeling the slope at that point, and now it's gonna, when I change it to a 2, if I can get it to slide, yeah, it models the concavity at that point, and then we get to the third derivative and the fourth derivative, and I hope you notice this little tail on the left that's wagging. Let's go back for a second. There's a tail over here that's gonna wag. And as I approach infinity, that little tail is gonna go, and it's gonna go further and further out, and eventually we're gonna run out of computational power and we're not gonna be able to do it, because consider what's happening. If I go all the way to 100, then for every x value on here, we have to raise it to the 100 and divide it by 100 factorial. Yeah, good luck with that. So we do that, and it becomes a better and better approximation. So notice that the blue and the red have come together, not politically, but the blue and the red have come together, and they are almost exactly perfect. Actually, we could zoom in and zoom in and zoom in, and computationally, it is such a good approximation that it can't tell a difference for very high values up here. So as this approaches infinity, it gets really good. But here's where we're going with this. The radius of convergence would mean if I truly went to infinity, would this be a good approximation everywhere, or would it just be a good approximation somewhere? All right, so we're going to take this up pretty high. We're going to go all the way out to 100, which is a far cry from infinity, but for our purposes, it's pretty good. And when we do that, we have this right here. So it's really good. I mean, this is almost a perfect approximation. This is great up to a point. And so let's raise this higher. And if we could truly go to infinity, does it continually stretch out forever? Let's take this to 200. And when we do, it gets further and further out. Where is it? There's a point where it kind of falls apart. Can't tell. All right. Apparently I have reached a threshold here. Nevertheless, it's a great approximation. And it looked like the further we dragged this out, the more this thing was coming out to the edge. And that means that our infinite sum is such a good approximation everywhere that my, new phrase, radius of convergence is infinity. All right. Here's what that means. My approximation will always work there, because it's built to do that. So my approximation always works there. However, my approximation, if I take it all the way out to infinity, does it work everywhere, or does it just work in a certain area? So this one actually is going to work everywhere, because as I drag this out and infinity truly, well, it approaches infinity. As we do this, this is a really good approximation in a lot of places, all over the place. So let me show you one that's not, and this will make sense. All right, here is a function. Let's make this one bold. Here's a function that we have right there. And what we're going to do with this is approximate it using this series. Trust me, this is the correct series that approximates it. And when we do that, probably hear some drilling in the background, ignore it. When we do that, we're going to see that the further out I drag this, it doesn't keep going like, we had that tail that was wagging and it kept going out further. The further we do this, it's not necessarily going to, the further we do this, it's not necessarily going to converge everywhere. It's going to converge up to a point. So let's drag this out here. And when we do, you're going to kind of see that as we approach where x equals 2, then it's never going to get beyond that. Never going to go beyond that. It's going to get like really close and right up to it. And so the purpose of this lesson is to determine how good our approximation is. Let me rephrase that. The purpose of this lesson is to determine the intervals on which my approximation will work. On the previous example, if I could truly go out to infinity, then my approximation will work everywhere. And from my center at 0, because this is centered at 0, from my center, my radius of convergence is infinity, because I could go forever out and forever back, and it works. But for this one, my radius of convergence is 2. And here's why. This is centered at 0. And because it was centered at 0, and I realize that I'm going out to 2 and no further, and there's clearly a discontinuity at -2, then I have this interval of convergence where this sum converges to the actual function it's approximating, but it only works from here to here. So beyond here, it is the worst approximation ever. It's not going to work. So let's go back to the sheet for a second, and I'm going to make some sense of what's about to happen, and then we're going to work through several examples. All right, for a power series centered at C, precisely one of the following is true, and we have talked about all three of these actually, and there are three things. The series converges only at C. So wherever you're centered, there is the possibility that it is the worst approximation, and it only converges at the point where you are trying to center that approximation. That can happen. There also could be some real number r greater than 0 such that the series converges absolutely, and this looks a little bit messed up, but let me put it into terms we just saw. That means that function you just saw that only went from -2 to 2, and that was the best our approximation could get, that's what this means. So my radius of convergence would be 2 in this case. Or that first thing we saw with e to the x, the series converges absolutely for all x. So if I could truly count to infinity and truly compute it to infinity, then I would have the best, most beautiful approximation that would be perfect, and it would converge to the actual function. So here's my function, and then I've got this thing going on, and then I'm able to take it all the way to infinity, and it is the exact same thing forever in this direction, forever in that direction. It'd be perfect. Okay? So again, here are your three options. Maybe your series converges only at that one point where it's centered. Maybe it converges somewhere in some radius, an x-type radius, from your center, or maybe it converges everywhere. And you're going to see examples of all three as we work through some examples.